All right, everybody, welcome back. Shout out Joy. I did remember to start the video, so I've grown. I have I'm reminding myself to start the video. I'm becoming self-sufficient. All right. I was going to say this a minute ago, but I want to say this before we start. For your calculators, guys, if there's ever anything going wrong with your calculator, like during a quiz or test, I can help you with a calculator issue. I can't show you how to do something on your calculator during a quiz or test, but I can like troubleshoot an issue, like if it froze or something, or something's not showing up and it should. I can help you with that sort of thing, but you can't walk up to me and be like, I don't remember how to do this on my calculator. I'm gonna be like, oh, that's hard. So just know that I can assist you with troubleshooting issues, like technical issues with your calculator during a quiz or test. But if it's something like, going through a process, I can't really help you with that. Okay, so we're going to be using our graphing calculators. This test that is coming up here on Thursday is fully calculator. You can use your calculators for the entire thing. It's not just the red calculators. You can use your calculators. It's full graphing calculators. So make sure you bring your graphing calculators with you on Thursday. Really, honestly, you should really bring them from here on out every single day. You're going to need your calculators pretty much every day once we get past that. I don't want to have to remind you to bring them because I'd be like saying it here and not enough. Just bring your calculators. Okay, so on this, within this chapter 1, we're talking about all the different things that we may cover during this year, and it's kind of like giving you like a foreshadowing a little bit. I've been saying all along in chapter 2 in algebra 2 that it's kind of an exploration in functions, all these different types of functions. And today is kind of giving you like a snapshot of what's to come. Okay, so we're going to talk about parent functions. So what is a parent function? Well, similar to the way the numbers are classified into sets based on common characteristics, like we can say, integers are all positive, negative, whole numbers. We can say that whole numbers are all all numbers starting with 0 on up. Natural numbers are the counting numbers, 1, 2, no decimals. Rational numbers are ones that can be written as a fraction. We have numbers that are classified into certain names based on their characteristics. The same thing is true for functions. We can classify functions based on their characteristics. Okay. Now, when we talk about function families, okay, we talk about function families. I'm going to say, okay, like the linear family, or the polynomial family, or the square root family, or the rational family. No, that's just kind of like all of them grouped together. But when I talk about a specific parent function, I'm talking about the most basic function that you could possibly get within that family. Okay. Now, the cool thing is that every single type of function that you could get, anything of that family, is just basically a transformation of that parent. Say the quadratic parent. We'll look at that in a second. It's just x squared. Okay. The quadratic parent, just x squared. If you wanted to create any quadratic possible, it's really just a set of transformations that had happened to it. Stretches, compressions, shifts, reflections, and so on, right? Just probably a combination of a lot of them, depending upon what it looks like. Okay. But the parent function is just basically the simplest function within that family. Functions in the same family are transformations of their parent function. So let's talk about this. Oh, I got this all covered up and you can see it all. So I'm just going to go take a moment and delete away all of these boxes. Actually, you know what? I'll go through family by family. First one is the constant family. The constant family. This is the most basic family that you could possibly get. The rule is just basically, now, when I say the rule, you can consider this like the parent function. Okay? This is really the parent function. F of x is equal to c, where c is just a constant. C is just a number. Like f of x is equal to 7. F of x is equal to 2. I don't know. Just pick a number. When it's just a constant, just a number, the graph is just a horizontal line. Okay, it shifts up or down, but dependent upon the value of c, whether that is positive or negative. The domain is always going to be all real numbers with that because it's going to go forever to the left and forever to the right. The range is dependent upon the c value. Okay, because obviously, if this is a horizontal line, say, I don't know, at 1, right? Then the y value, the only possible y values I could get are just 1, right? 3, 1, 4, 1, negative 5, 1, negative 6, 1, 0, 1. The y value is always stuck at 1. So that means the range is always 1, which includes also the y-intercept. The y-intercept is 0, that number. So in this case, it's 0, c, or 0, 1 in that example that I was talking about. Okay, so let's talk about the linear type, the next level up. Okay, now we introduce a variable into the mix. The rule, I don't want to have it too. The rule would look just like f of x is equal to x. That's the most basic linear function you could get, right? F of x is x. Done. Y equals x, right? Whatever x is, y is the same thing. X is 1, y is 1. X is 2, y is 2. X is 3, y is 3. So, okay. That just makes a diagonal line running through the first and third quadrants. Okay. X is negative 5, y is negative 5, right? It just runs exactly with a slope of 1 through the first and third quadrants. The domain is going to be all real numbers because I am again going forever left and right. And this time the range is not restricted because it will go forever up and down as well. So that's an all real numbers type deal. Now, where does this cross the x-axis or the y-axis? At the origin point, right? It runs through 0, 0. Okay. Why are we talking about this? This y-intercept is going to be a very important point for all of our transformations. So it's good to know where the parent function crosses the y-axis, because the y-axis, because that that will tell you, the transformations will be applied to the y-intercept often. Okay. All right, the quadratic. I just talked about it a second ago. Y equals x squared, or f of x is equal to x squared. That's our most basic quadratic function. Okay, f of x is equal to x squared, or y is equal to x squared. So if I plug in 1, I get 4. I plug in 2, I plug in 1, I get 1. I plug in 2, I get 4. I plug in 3, I get 9. I plug in 4, I get 16, and so on and so forth. What happens if I plug in negatives in here? Turns back positive, right? Plug in negative 2, it turns positive 4. Plug in negative 3, it turns positive 9. So the graph looks like this parabolic shape. It looks like a parabola going up on not only the right side, but also the left side as well. Okay, the domain is all real numbers again, but the range, and again, I'm only talking about this parent function, domain and range. If I transform it, then the domain and range may change, but this is just the parent, just the most basic one. The range, it looks like it's greater than or equal to 0, and that will change depending upon where the vertex of the parabola is. Don't worry, we'll take a whole chapter on quadratics, and we'll talk about that then. This one also goes through the origin point. Okay, it also goes through the origin point. Okay, the cubic function. The cubic function. F of x is equal to x to the third. This is that kind of weird-looking curved shape that goes through the middle of the graph. Yeah. So basically, if I have the parabola, I am just going to rotate that one side of the parabola downward. I'm going to take this left side of the parabola, this left tail, and make it, instead of it going upward, I'm going to make it go downward. And it actually goes steeper than a quadratic because it's cubic. Like if I plug in 1, I get 1. Okay, that's the same coordinate. But if I plug in 2, I get 8, not 4. If I plug in 3, well, that's 3 times 3 times 3, that's 27, not 9. So it increases a little bit faster, both on the left side and the right side. The domain, in this case, is still all real numbers, but the range is now all real numbers as well. Okay, it's no, I can get negatives now, right? If I plug in negative 2 to the third power, I can get negative 8. The negatives will come back up again. Okay, this one also intersects the origin point. Last one we'll talk about on this slide is the square root one. The square root one. F of x is equal to the square root of x. This one, okay, so if I take the square root of a number, square root of 9, 3. Square root of 25, 5. Right? So if I plug in those values, it's going to decrease the y value. So take a look at what's going to happen. The y value is going to decrease as we go ahead. Right? If I increase the x values, it will kind of tail off a little bit on my y values. Okay? What don't you see? I don't see the bottom half of this curve, don't I? I mean, it almost should make sense that this is the inverse of a quadratic. I should see some sort of, tilted square, tilted quadratic, tilted parabola. But I don't see the right side. I don't see the right tail. Okay. Why not? Well, what gives you a negative out when I get a square root? Like thinking about the y values. If I plug in an x value, which x values will give me a negative out here? None, right? So what would happen if I plug in a negative? Is that defined? Like square root of negative 9? Is that negative 3? No, that's actually 3i, which we'll talk about a little bit later. So we have to restrict the domain and range a little bit. X has to be greater than or equal to 0, and y has to be greater than or equal to 0. Okay? Now, why do I restrict the domain? Well, if I had not restricted the domain, it would look like this. Guys, is that a function? Then this would ruin this whole table, right? Okay? It has to be a function. So therefore, I have to restrict the domain. I only want the top half of the graph. I only want the positive root, the principal root. Okay? And this one actually also runs through 0, 0. It's interesting that all of those run through the origin point. The reason being is there's no transformation that had happened yet. Okay? Now, I'm not saying that all parent functions will run through the origin point. I'm just saying these particular ones will all run through the origin point. Okay, enough of me talking. Let's get to your calculators here. Identify the parent function for g from its function rule. Then graph on your calculator and describe what transformation on the parent function it represents. Also state the domain and range. All right, first thing that I want to take a look at is what's the parent function? We don't even need to graph it yet. What is the parent function here? Maybe identify the function family. What type of function is this? What do you think? Colton? Linear, right? There's no x squareds going on. Of the 5 that we have listed there, this one looks linear. Okay, so what's the parent function of the linear? F of x is equal to x, right? So the parent is f of x is equal to x. Please don't say linear. That's the family name. I want the parent function. Okay, identify the parent function. Check. Then graph g on your calculator and describe what transformation of the parent function it represents. Okay, let me open up my calculator here. Now, to graph anything on these graphing calculators, you're going to go into your y equals button. Okay, you're going to go into your y equals. That's where you graph everything. So I'm going to hit my y equals button, and I've got some funky stuff there, so I'm going to clear out everything that's there. I should have just reset my calculator, but that's okay. Okay, so your screen probably looks like this, right? So all I'm going to do is plug in, this says y equals, but g of x is same thing as y, right? This is just in function notation. Your calculator is not in function notation. So it's y equals x minus 3. X minus 3. That x button is right there. That button gets you all the variables, okay? And all the different types of modes that your calculator can be in. Okay, you can put in a theta there, you can put a little n. Those are all based on you can put your calculator in a polar mode or parametric mode or different modes. Okay, now here's what I'm going to do. I am not only going to graph the transformed function, but I am also going to graph the parent as well, because I want to see what type of transformation it has. Okay. Over here on the left side, if I keep moving to the left, do you see how it's blinking now over here? I don't know what it looks like on your calculators, but I can change the way that line looks. I can make it a thick line. I can make it a shaded line, which is inequalities. I can make it I can make it trace along with a little circle as it goes along. I can make it just the circle. I could make it a big dotted line, or it can go back to this regular line. So I'm just going to do that. Now, to get your calculator always back to a normal standard window, you hit this zoom button, top middle button, and then do we all see zoom standard, Z standard? That's your normal 10 by 10 window. So if I hit zoom 6, or just scroll down to it. It'll graph on my normal 10 by 10 window. Okay. So here's my graph. Right. You could have just hit graph. The reason I hit Zoom 6 is because I had some funky stuff going on in my calculator, and I probably had messed up the window at some point. If you're, anybody play calculator games anymore? Man, back in high school, like we didn't have cell phones. So it was like, oh man, I'm gonna play Uncle Worm on my calculator. Yes. Anyway, here are my two functions. Okay. If you ever wanted to regraph, just go back into y equals and just like put another number in there, like put x back in, just retype something back in, and then you hit the graph button again, and you can see it graph again. So my first function, this was f. We'll call this f, and this was g, right? My first function was the transformed one. My second one that came through, that was my parent. So what's the type of transformation that's happening here? I have no context. Okay, I have no context like I used to have on that word problem where I knew exactly what was happening in terms of the coordinates. I have no context going on. So what do you think the transformation is? What do you think, Colton?
Translation.
How much? What direction and how much?
By negative.
Right or, so you're saying down?
Yeah.
So shift down 3, right? Okay, he says down 3. Does anybody see anything different? That's totally fine. That's one of the acceptable answers. What's the other acceptable answer?
To the right 3.
To the right 3. Yeah, I remember talking about this linear thing where, we don't really know what's happening in the transformations because we don't see the context going on. We weren't told what the transformation was. So just based on the look of the graph, I see that it could be down 3 or it could be right 3. It's interesting that there's a minus sign and I say that it could be right 3. That will come up a little bit later. Later as in when we get to the linear transformation chapter. Okay, now then graph, done. Describe what transformation, done. State the domain and range. State the domain and range. What is the domain of this function? Will it go on forever left and right? Yes. Will it go on forever up and down? Yes. So the domain and the range are both all real numbers. Especially because it's a linear function. Okay, so let's keep it moving. You guys have x squared plus 5. X squared plus 5. Okay, so first thing that we should do is identify the parent. So what type of function do you think this is? Out of these here. What type of function? Go ahead, Colton.
Quadratic.
It's quadratic, right? It's quadratic. So we could say that the parent is f of x is equal to x squared. Okay, hey guys, before you graph it, I always like to try this. What do you think is going to happen? What do you think is going to happen? If this top one went down 3, what do you think is going to happen? Anybody got any guesses? Go ahead, Cole. You think? Let's see. Let's test this out. He's like, I already graphed it. I know for sure. Okay, I'm going to say x squared. Squared button is on the left side, about halfway down. X squared plus 5. And then I'm going to just put in x squared. So you guys with your fancy colors in there, can you change the color on each one? Or you can see the color on each one on the left side. And you can scroll over there and change it too. See, me, I have to be like very careful of which one goes first and which one goes second so that I can tell the difference between the two. You fancy, color graphing calculators, those ones are the nice ones there. You can see exactly what's going on. I'm going to hit graph here, and I'm going to see, okay, this is my transformed, this is my old. Okay. So I see here, this is my F, and this is my G. Okay, so did we confirm the up 5? Yes. Up 5. Vertical shift, up 5. I'm okay with this saying up 5. Could this be anything else? Can it be a left or right like the other one was? Nope, definitely not a left or right. What somebody always says, oh, couldn't this be like a vertical stretch? Could it be a vertical stretch? The answer is no, because what point changed? We're across the origin point, right? The vertex point or the y-intercept point. If the y-intercept changes, we talked about this last week, the y-intercept changes, a vertical stretch does not change that y-intercept, basically, right? And the y-intercept changed, so this can't be a vertical stretch. All right, so this is an up 5. What else did we have to do? We had to, we graphed on a calculator, describe the transformation, state the domain and range. State the domain and the range. What is the domain here of G? What is the domain of G? Will it go forever left and right still? Yeah, the domain does not change there. The domain is all real numbers. Now, let's be very careful. Remember that I'm only focusing on the domain, the range of the transformed function. So if you'd like to, you could go back in and like turn off the parent. Okay, if you just unhighlight the equal sign, it will only graph the highlighted equal sign ones. So I'm only focused on this, right? What's the range of this? What's the range of this? Oh, come on, somebody other than Colton. Come on now. Come on now, people. Don't make me draw at random. What's the range? Ms. Walls.
Greater than or equal to 5.
Very good. Greater than or equal to 5. Now, I'd like us to put it in some sort of notation. I'm going to try to be a little bit more picky about this. We'll get lazy a little bit later on in the year, and we'll just say greater than or equal to 5 and an inequality. Let's write that in interval notation. 5 to infinity, right? 5 to infinity. Greater than or equal to 5. If I wanted to write it in set builder notation, x such that x is greater than or equal to 5. So if you're really stuck on that inequality thing, just write it in set builder. But I'd like to push us toward using interval notation. Mr. Delap in CCP pre-calc like strictly uses interval notation. So it'd be good to push us toward that anyway. All right, let's keep it going. X to the third plus 2. So what do we think about this one? What type of family is this one? Cubic, right. So that would mean that our parent would be f of x is equal to x to the third. So there's our parent function. So let's graph. Now, what do we think the plus 2 is going to do? Up 2, maybe? I don't know. Let's see. Okay, I'll go back into my y equals. I'll say x to the third. The caret up button is right here underneath clear. Yeah, that'll show a raised to the power of. Some of you guys, it may look different when you go and do that. It like brings up a little box up there, and you can like type in there. Then you have to arrow over to get back down to do the plus 2. Okay. My calculator not like that. Mine's like the old version of this. Okay, and then I've got x to the third, x to the third, and then I already highlighted it back again, saying like, okay, yeah, you do want to graph that both. There's my new, there's my parent. Okay, so this is F, and this is G. Wait a sec. It didn't just go up 2. What did I did 5. What the heck am I doing? I was going to say. Plus 5 was the last one. Here we go. That's much better. I'll just put you over top there. This is G on the left side. This is F on the right side. Now, it may be hard to see based on just the pixels that are there, but take a look. Remember, I talked about that origin point being extremely important, right? Here was the parent origin point, right? That's where it crossed the y-axis. Where does it now cross the y-axis? 2 units up. That's the new y-intercept. So we could say up 2. Okay, domain and range there. Will it go forever left and right? Yes, it will slowly creep forever left and right. But yes, it will continue. basically this, for my domain, you can also think about, are there any restrictions on what I plug into this thing? Like, could I plug in 1 million if I wanted to? Yeah, it's gonna give me a really big number, right? Could I plug in negative 1 million if I wanted to? Yeah. So the domain is all real numbers. Is the range all real numbers as well? Yeah, that one's gonna go forever up and down as well. Oops, forgot mine. Oops, that's a poorly written domain. Last one on this page. There we go. F of x is equal to the square root of x plus 3. All right. So, what do you think the parent function is going to be here? I say the square root of x plus 3, so there's a family there, right? Okay. So what's the parent? F of x equals square root of x. Parent is f of x equals square root of x. All right, so let's, actually, before we graph, what do you think is going to happen with this plus 3? Tendency is to try to say, oh, it's probably going to go up 3 because I'm adding. We'll see. Let's see. I'm going to clear out anything that's there and do the square root of. Square root is right above x squared, right? Hit second and then x squared to get that square root button. The square root of x plus 3, close parentheses. And then the square root of x. Close parentheses. Graph. Graph. Needed to be voice command. Remember that this is f and this is g over here. Oh, shoot. Yeah. Now, what happened? What actually happened going from parent to new? Did it go up? Where did it move to? Move left. How much? Well, take a look at your y-intercept right there. 1, 2, 3 to the left. Left, 3. Okay, so my domain also gets shifted to the left 3. My domain also gets shifted to the left 3, from -3 to infinity. Or if you wanted to, again, set all numbers x such that x is greater than or equal to -3. Now for my range, okay, for my range, did it shift anything up or down from my parent? No. So therefore, my range is going to be the exact same thing that my range was, greater than or equal to 0. If I wanted to, in my set builder, set of all numbers x such that x is greater than or equal to 0. Okay, let's flip it over and do these couple problems here. Graph the data from this set of ordered pairs, describe the parent function and the transformation that best approximates. I'm looking for the best estimation that you can get on these functions. Okay, best estimation. Graph the data. So, okay, let's graph it. I've got -2, 12. Do this in red. -2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got -1, 3. I've got 0, 0. I've got 1, 3. And I've got 2, 12. All right. So I am going to, I know I really shouldn't because that's my data set, but so I'll do it in yellow because this is kind of like breaking the rules here. I'm just going to connect the dots to see what type of to see what type of function this is. What type of function do you think that is? What's that look like to you guys? That looks quadratic, right? I would agree with that. Okay, so the parent is f of x is equal to x squared. Now, what type of transformation do you see? Is it a shift at all? Do I move the origin? No. So what type of transformation do you think it is? It's obviously not a reflection. So I'm stuck to stretch or compression, right? So what do you think it is? What do you think it is? In my opinion, this looks like to me vertical stretch. Vertical stretch. Because if you think about where the parent was, I'll put it in purple. If I plug in 0, 0 there, 1, 1, 2, 4, 3, 9, right? Somewhere up here. 4, 5, 6, 7, 8, 9, right? There's the right side. Just taking a look at the right side, doesn't it look like it got, look, 1 to there, 2 to there, 3 to way up there, right? If I continue the pattern going, right? So it looks to me like a vertical stretch. If you're just estimating, I mean, I don't really need the, I could say vertical stretch by 3. You can estimate that by 3. How do I see that? Look at 1, 1. What did 1, 1 get transformed into? 1, 3. This would have been 2, 4 for my parents, right? This got transformed into 2, 12. Okay, the y values are multiplied by 3. Vertical stretch by 3. Okay. And the last one here, graph the relationship from year to sales in millions of dollars and identify which parent function best describes the data. Then use the graph to estimate when the cumulative sales would reach 10 million. Basically making a scatter plot here, right? We'll do this a lot this year, where we'll make a scatter plot and then figure out what type of function is fitting the data. And then based on that fit, we'll interpret the results. Okay, so I got 5 years. It looks like, let's say year 1, year 2, year 3, year 4, oh, wait, no, we want to, oh no, we're okay. Year 5. All right, and let's go up. Okay, we'll go by ones for the millions of sales. Year 1, 0.6, somewhere right there. Year 2, 1.8, somewhere right there. Year 3, 4.2, 1, 2, 3, 4.2, somewhere right there. 7.8 for year 4, 1, 2, 3, 4, 5, 6, 7.8. And 12.6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, 12.6. Halfway through that box. Okay. Does this look linear? If I put a straight line on this, would that be okay? Like if I do this, like okay, where am I gonna put it, right? Straight line really doesn't fit this graph very well, does it? So what would this be? What do you think? I think there's 2 options. I'd say either quadratic or cubic. Look at the right side of the quadratic and the right side of cubic. Don't you see the right side tail? Do I care about negatives in this? No. And isn't the only difference between quadratic and cubic the negatives? So, well, I shouldn't say that. Obviously, the cubic is going to increase greater with as my x values increase. But generally with the curve, okay, to me, I'm going to say probably quadratic. Probably quadratic. Okay, that to me looks quadratic. It looks a little bit more rounded out, not so steep as a cubic would be. Okay, then use the graph to estimate when the cumulative sales reached $10 million. Okay, I'm going to go here and I'm going to say, where is 10 million on my y values? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, somewhere around right there. Let's say that's 1, 2, 3, 4.5 years. Year 4.5. Questions about that? Trust me, we will learn more and more about our calculators as the year goes on. I'll kind of teach you as we go, teach you the things that you need to learn. I will tell you this, if you're ever struggling with like, okay, how do I do this in my calculator? Google is a great tool. If I'm not around, obviously come and ask me if you can. But, just search, okay, how do I do this in a TI-83, and there's probably YouTube video out there for it. But yeah, we'll do all sorts of things. Okay, I gotta stop the video. See you, everybody. So long, folks at home.